Hello, everyone, and welcome to another year of Simon Says. So this year we have a new theme called the Elements of Creation, where we're going to be looking at basically important substances that make up the universe that God's made. And rather than looking at a specific scientific idea or a principle, looking at a substance and how all those principles are at play in terms of how it plays a role in our universe. And so first up, I figured we start with something really important. Water, can't live without it. And we'll have a look at the different ways that God uses water on Earth. It's in its particular importance to life. It's not an element scientifically per se, but it's an important substituent, a building block of the world that we live in. So let's dive in. All right, so today we're going to have a look at the key properties of what makes water so great. And then we're going to have a look at a bit of its chemical structure to help explain why it's so great. What about its structure allows it to do those things? And then lastly, what is water's impact on life and why we can't live without it? So first, let's have a look at the key properties. Let's have a look at why water is so interesting in the first place. What makes it great? And so water is a molecule. It's made up of two hydrogen atoms and one oxygen atom, hence its name H2O. Two H's for hydrogen and one O for oxygen. That's why we call it H2O, and that's broken into the public consciousness despite being a chemical formula. And so it's tasteless, odorless, colorless, which sounds a bit boring, but it's the only substance on Earth that actually exists as a solid, liquid, and gas on the Earth's surface. So other substances are only as a rock or a solid, or only as a gas or a liquid, maybe a couple, but not all three. And so from a general perspective, it's cheap, it's non-toxic, can store a lot of heat. That's why ice boxes were really important for preserving foods, and why we use freezers now. It absorbs microwaves. That helps us to cook our food in the microwave because it absorbs that energy to heat up nicely for our food. And obviously it's really important for life. And so because it's cheap and non-toxic and stores heat, it's great, cool, and engineers love it. It has a lot of really practical uses. And there's lots of it out there. Our oceans contain 1.38 times 10 to the 9 kilometers cubed of water. So 10 to the 9 being billions, so 1.38 billion. And that's billions of kilometers. Imagine a kilometer, and then imagine another square, so a square kilometer, and then a kilometer straight up to make a cube. That's a cubic kilometer. 1.38 billion of those, lots and lots of water. And so scientifically, it has some additional helpful properties too. It has high electronegativity. It's got a high boiling point for such a small molecule. It's got high surface tension, high cohesion and adhesion, low vapor pressure, high polarity. It's non-corrosive, has high heat capacity. It's got very unusual density. It's a universal solvent. It's amphoteric, which means it can contribute to being an acid or base. It mixes with lots of liquids like alcohols, but not oils, and it participates in a range of important chemical reactions. So we're going to talk about some of those today, but not all of them, or we'd be here all week. And also, interestingly, pure water is an electrical insulator. We tend to think of water as conducting electricity, but pure water does not. It's only when ions are present, which is nearly always, that it then becomes an electrical conductor. And so if you've ever looked at the side of your bottled water, it's got a list of all those minerals in there. Those minerals are what helps the water to conduct electricity. All right, so we've had a look at some bits and bobs about why water is really cool and important, but how? Like, why is it good? What gives it these key properties? And I'll give you a clue, it's chemistry. Let's have a look. So water has a very unusual structure and physical shape. And so part of this is the properties of the structure allow it to hydrogen bond easily. So we're going to have a look at what hydrogen bonds are. But basically, it's got this little bit of extra bonding that not all substances do. And this gives it unusually strong bonds between molecules. And this explains a lot of the characteristics from before. And we're going to have a look at some of those in some more detail. And so this right here is an example of the polar covalent bonds, which make up water. So I've got the big red oxygen atom in the middle, and we've got the two little blue hydrogen atoms over here. And they come together to form this H2O on the right-hand side, which we know and love. And so oxygen in this large outer ring, you can see it's got 6 little circles on it. They're electrons. And oxygen dearly wants to have 8 electrons on that outer ring. It's unhappy when it has 6. Whereas hydrogen, it wants to have either 2 in its ring or none. And so these hydrogens are a bit unhappy. They've only got 1. They like to have 2 electrons in their ring. Down here, he'd like to have 2 electrons in his ring. And oxygen here would like to have 8 electrons in its outer ring. And so by sharing through a covalent bond, so co like cooperating and valence like availability, by sharing availability of their electrons, they come together and they can all be happy. So my oxygen on the outer ring, it now has 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outer ring. It is happy. My hydrogen atoms, they have 1, 2 on their ring and 1, 2 down here in their ring. They are happy too. So everybody's happy. They have the ideal number of electrons in their outer ring through this shared polar covalent bond. But, and there is a but. So because they're sharing, they don't have what they want all the time. They've kind of got this shared custody thing going on. They're happy some of the time. They're not happy all of the time. And basically this results in partial charges because when a substance has not enough electrons, it will be slightly positive. And when it has too many electrons, it will be slightly negative. And so we can see here that this results in a bent structure of water because all the positive charges want to repel each other. All the negative charges want to repel each other. All the positives want to be with the negatives because we know opposites attract. And when that all kind of settles down and they come to a truce, they're all optimally aligned for their likes and dislikes. We end up with this bent structure of water. It's a bit like a boomerang. And not only that, we end up with these partial charges at particular points, particular places in the molecule. And so it's these partial charges at very specific places, which allows it to associate with either itself or other objects. And that is what contributes to its really important characteristics. And so these partial charges facilitate hydrogen bonding. I'm going to be talking about hydrogen bonding a lot today. So that's why water is amazing. Let's have a look at how it puts these characteristics to the test, what it actually does in the world around us. And so the first one is adhesion and cohesion. So cohesion is a word that we use to describe when molecules are attracted to other molecules of the same kind. And so you may have noticed when there's water droplets on a windscreen in the car or when it's raining or something like that, there are lots of individual water droplets spread out. But if you get them close to each other, look, they'll join up, they'll come together, they'll kind of jump to be friends together. And so that's a result of cohesion because the water molecules are attracted to other water molecules too. All the water molecules want to be together. They want to form big groups. And this is because of that partial charging, which results in hydrogen bonds. So chemically, they're attracted to each other and they'll stick together fairly well. And we call this cohesion. And that explains why you can move your finger around and you can make a big blob of water because every bit of water you touch is going to join the big blob through this mechanism of cohesion. And so this explains why we see surface tension. So you can see my little cup there. I don't know if you've ever filled a cup right to the top, but you can actually get water to sit above the top of the cup. It can actually spill over a bit without actually spilling. So this is as a result of surface tension. So at the surface, there's a little bit of a force holding things together. It's tense, it's keeping things tight and glued together. And that's as a result of this cohesion due to hydrogen bonds. And so it allows us to fill our cup a little bit higher. It's also the reason that belly flops hurt because you jump in and boom, the water doesn't want to separate for you. And so it hurts. It's like hitting a brick wall for a moment. And it also allows the weight of light objects to actually sit on top. That water tension as a result of cohesion is actually strong enough to allow little things to sit on top. So this little bug here, he can stand on the water as long as he's very light and that weight is spread out. And there's even lizards that can run quickly across the top of the water by using this in very a short temporary way with each step, but it's enough to keep it going. And so that surface tension results due to the cohesion, which is because of those hydrogen bonds, because of its chemical structure. So I mentioned adhesion as well. Adhesion is related. So adhesion is when molecules are attracted to a different type of molecule. So rather than water hanging out with all its water mates, it can actually make new friends with things that aren't water, and we call that adhesion. And so because this is a charged interaction, the hydrogen bonds, anything that's going to interact with a charge is going to have some sort of interaction with the water. And so this is actually really important for water movement inside plants. And so this adhesion and cohesion effect, they cause a little chain reaction, if you will, and it can actually transport water upwards through the plant. It absorbs water through the roots at the bottom, and it can then move up through the stem, through these tubes called the xylem. And as capillary action happens as a result of this, it actually allows the water to flow upwards against gravity, and it doesn't cost the plant any energy. It just happens naturally because that's what water and other substances are happy to do. That's just how they roll. And so it means the plant isn't spending energy pumping all day, every day. It just happens just by magic, if you will, because of the processes that God has designed. So here is a little graphic of that, of adhesion and cohesion in action. And so this is a part of xylem in the plant. And so the water will adhere to the walls of the plant through adhesion, so water sticking to something else. But also because there's other water in the tube, the water is going to attract other water. So I can pull the water to the water that's on the wall. And so through this chain reaction of that process repeating, it can actually allow the water to climb up the xylem without any energy, just because water is happy to stick to itself, and it's also happy to stick to other things. And it's happening through this hydrogen bonding here. We see these small positive charges on the hydrogen being attracted to these small negative charges on the oxygen. So they're attached from oxygen to hydrogen, and vice versa. And so it allows this energy-free movement of water through plants, which is awesome. All right, next one. Water is also a really handy solvent, and we call it the universal solvent because it does it all. It slices, it dices, it does everything. And so water's polar nature, so having those charges, that hydrogen bonding, those small pluses and minuses, it allows a lot of substances to easily dissolve in it. So if something can have stuff dissolved in it, we call it a solvent. If I'm adding sugar to my water, I'm going to make a cup of tea or coffee. That water is acting as a solvent for my solute, the sugar. And so it's dissolving, and it's happening as a result of the polar nature. It's being helped by those positive and negative charges. And so there are ionic compounds out there. They are compounds which are held together by charge bonds. So a positive and negative, they've come together, opposites attracting to make a new substance. But when those substances are put into water, because water also has this wide variety of positive and negative charges, those positives and negatives can break up. They can just go into the water, and that's what allows it to dissociate from itself, those two parts of that compound, and then go to associate with the water particles instead. So we're going to talk about an example. We're going to talk about table salt, the stuff you put on your chips. Scientifically, it's called sodium chloride. And so like I mentioned before, there's a positive here on the sodium there. And there's a negative on the chloride. Positive and negative, opposites attract. When they come together, they make salt. So sodium is a gray metal. It's like a metal, except when you drop it in water, it explodes. And chlorine is a gas. It's a green gas. You breathe it in, it will kill you. But for some reason, in their ionic forms, when they come together, they make salt, and you can eat it on your chips. That chemistry is weird like that. And then when we add it to water, it disassociates, moves into the water, and we get salty water. They're still there, but the water has the capacity to hold a lot of the salts due to the nature of those charges. So normally salt has a crystal structure, which just means they're all stacked together in a nice uniform shape like this. So my positive sodiums in blue here are next to my negative chlorines in green, and they stack in this alternating pattern, positive, negative, and then from bottom to top as well, positive, negative. We call this a crystal structure. And so you can see that when you put that in water, when water also has those positive and negative charges, here's my red and white boomerangs, the water. So the positive charges on the hydrogen and the red negative charged oxygen. We can see that the big blue sodium ions, which are positive, they're going to be happily hanging out with the negative red oxygens. And the big green chlorines, they're going to happily hang around with the small white positively charged hydrogens, because positives and negatives, opposites attract. They like to hang out. And so that chemistry is what allows water to be what we call a universal solvent. It's really good at having things dissolve in it. And it's all because of those charge properties. And so this is really helpful because it allows water to be the basis for cells. You may have heard that your body is made up of basically 70, 60% water, thereabouts. It's because our cells are made up of roughly that much water. Why? Because water is helpful for moving stuff around. So a cell is basically a cell wall. It's just a big bag of stuff, and inside it has all the little bits and bobs that it needs to do cell stuff. And for a cell to do cell stuff, it also needs food like salts and sugars. It needs oxygen to help it to make energy, and it needs to cart energy around in the form of chemicals too. And cells also create wastes, and those wastes need to be removed. We need to get carbon dioxide out of our systems and back to our lungs so we can breathe it out. And so by having them dissolving in water, all of these things can move around. They can just randomly bump around into the place that they need to be because they can just float around in the water until they come across where they're needed. And so all particles are always randomly moving. We call this Brownian motion. That's a result of their temperature. As something gets hotter, it just moves more. That's what temperature is. The average motion kinetic energy of a substance. And so they're always just moving randomly. And so those bits and bobs are going to get to where they need to go because they can just float around through the water. And so water, being a helpful universal solvent, allows our cells to function because they get the food they need, they get the energy need, and they can get rid of their waste just by floating around in the water so stuff gets to where it needs to go. And so moving outside the cells, thinking larger in terms of big groups of cells making tissues like cartilage, for example, water is also helpful because it insulates against temperature changes. So water has a high specific heat capacity, which means it can absorb a lot of heat energy without its temperature increasing. And so basically, if water is around, it's going to stop temperature change from happening quickly. And so that's really helpful, keeps us where we need to be because the human body wants to always sit at 37 degrees Celsius so that all our proteins and enzymes do the things that they are meant to do. So water helps with that. It can also be a shock absorber against impacts. You get whacked by something, you imagine lots of water inside you, that water is just going to float around a bit rather than things getting crushed and squished and broken like they might otherwise be. And it can also act as lubrication for movement, like in our joints. So in our joint space, there's water in there, among other things. But being a helpful liquid like that, it just helps things to move around so they're not grinding against each other if they're dry and crusty kind of thing. And that allows our joints to last longer so that we can use those joints for a long time to come. All right, so we talked a little bit about the cells and how water helps things to move around inside the cells. Water actually helps cells to even exist in the first place. So I mentioned that cells are basically just a big bag of water and stuff inside them. The lining of the bag is what we call a cell membrane. And a cell membrane needs water to exist as well. So cell membrane is made up of a whole bunch of what we call phospholipid molecules on the left-hand side here. And they look like a funny jellyfish. They got a little circle bit at the top, and then they've got tails. And so these tails are fats, and fats are very hydrophobic. They don't like water. They're not charged. They don't want this positive, negative stuff. They just want to do their own thing. Whereas at the top, the blue head is charged. It's hydrophilic. And so because it's charged, it's going to participate in that hydrogen bonding. It wants to be around water with its positive and negative charges. And so because phospholipids have this strange dual nature of being charged at the top, but uncharged at the bottom, when they interact with water, the top heads, they're happy to chill with water at the top here. Yay, yay, water. All the heads are hanging around the water. And then down here, all these heads are hanging out for water too. But the middle part, the fatty acid part, which does not want to hang around with water, it wants to hang around with its own kind. And so they'll actually just chill in the middle here. You'll have, they'll orient in a way so that those fatty acids are in the middle and those charged heads are on the outside. And so by doing this, they actually form this exclusive layer. There's the fatty acids in the middle who are kind of leaving everybody else out. And then you have the charged heads, which are chilling with water. And so because they naturally arrange themselves in this way due to the chemistry and what that wants to do, they actually organize themselves in a big long chain, which allows us to make that, the wall of that bag that holds a cell together, that cell membrane. And so even water just allows cells to exist in the first place, not just by moving stuff around inside, but causing a chemical cascade, which allows that bag of the cell to be formed to hold it all together in one piece. All right, so it keeps cells together, but it also does photosynthesis. We know that's really important. So basically all the energy we use on Earth came from the sun. So the sun's kind of important. It's not just from solar panels, it's from plants. Plants absorb the solar energy and they use that to help them to do photosynthesis. And so photosynthesis takes carbon dioxide, the stuff we breathe out, it mixes it with water and it makes sugar and oxygen that we need to breathe. Very important. So they take our waste products that we breathe out and a bit of water to make sugar, food, energy, and the stuff that we need to breathe with oxygen. So really, really important process, and water is literally an ingredient in that process. And so it's also true for the opposite of photosynthesis, going back the other way, which is cellular respiration. That's what we do. We breathe in the oxygen from the plants. We eat lots of sugar, lots of foods for fuels. We then break down those fuels so that we can get energy. We need ATP to use as energy to do the things we do so that we can move and function. Makes a bit of heat as well to help us regulate our body temperature. And then our waste products are water and carbon dioxide. So we breathe out that carbon dioxide so the plants can take on that and start the cycle again. And we actually make about 10% of the water from our food, strangely enough. We think that we only get it from drinking, but breaking down our food, breaking down glucose and sugar actually generates a bit of the water in our bodies as well. So again, water, another really important participant in a really important reaction, because all the energy on Earth comes from the sun. All the energy on Earth was processed by plants using water as part of that. And for us to function and have energy and do what we do, we need to break it down to make water, and then the cycle begins again. All right, water is also useful for pH. You may have heard of pH. pH is a measure of how acidic something is, or how basic or how alkaline it is. So an acid is defined as something that donates hydrogen ions to a solution, and they tend to be very corrosive as a result. They inspire chemical reactions because anything with a plus wants to react and do stuff. And so battery acid has a lot of hydrogen ions floating around. It wants to react, and as it reacts, it will corrode things. So the inverse of that is a base, which is alkaline. They're also corrosive too, because they donate OH minus to a solution. And so because it's charged, it also wants to react and corrode with things, just in a chemically different way. So they're both dangerous. But water is in the middle. It's neutral with a pH of 7. So on a scale of 1 to 14, where 1 is acid, low numbers are acidic, 14 is alkaline, high numbers are alkaline. Water is smack bang in the middle at 7. We call that neutral, neither acidic or basic overall. And so the astute among you may have noticed that, the acidic parts are positive hydrogen ions and the alkaline parts are OH. What do you get if you mix an OH and a H? You get H2O, which is water. And so water, if you combine an acid and a base like this here, so that's hydrochloric acid and sodium hydroxide, if you combine those together, you'll get water and table salt. So we call this a neutralization reaction. Horrible, deadly acid, horrible, deadly base, mix them together, you get salt water, you can drink it, it's fine. One of my high school teachers had a friend in university who apparently did that reaction and drank it. All the power to him. I'm happy to just trust the scientists on this one. Yeah, but you can see that so water has this unique relationship with acids and bases as chemistry as well. And any acid and base coming together will form water and some kind of salt as a result. And so here is the pH table, which describes acidics from 1 or 0 to 14. So water in the middle is neutral. Here are some common examples of those things. So the really acidic things are like battery acid, stomach acid, or like soft drink and lemons. They're quite acidic. These things can give you like heartburn because there's too much acid in your stomach going on. Whereas on the other side, we basically have drain cleaners. They're really corrosive, so they're really good at getting rid of gunk and cleaning things. We've got drain cleaner, bleach, soap, antacids for your stomach, because if it's too acidic, we add a base to neutralize things out. And then more normal things in the middle, like blood, egg white, milk, coffee, that sort of stuff. So it gives you a perspective of the pH scale and how it works and how water is nice and neutral, happy sitting in the middle. All right, so in the body, we have pH. So our blood has a pH. Our blood can be moved to be slightly more acidic or slightly more basic than it is before, but our body will tightly regulate pH because pH will muck with all the chemical reactions in your body. It's like the weather for chemistry. It's cloudy today or it's sunny today. I'm going to do more reaction or I'm going to do less reaction. So it's really important that we have the right climate for the chemical reactions in our bodies. And our body does that by regulating pH very tightly. It aims to keep it between 7.35 and 7.45. So basically neutral and basically neutral. We don't want much wiggle room at all. And so that allows our bodies to do what it needs to do. And so we've got physiological pH for dummies on the right-hand side. You might have heard of acidification or alkalizing your body or alkaline water, all that kind of stuff, trying to manage your pH of your body. You can't. If you have kidneys and lungs, your body is going to do its best to keep in that small range of 0.1 pHs. And if you get above or below that, basically you're trending towards death. So there's no purpose in trying to acidify or alkalize your body because your body is working very hard to keep it in a very tight range all the time because that's important for the chemistry climate of your body so it can do what it needs to do. All right, so now we're going to have a look at water's density. So going back to, you might have learnt this in school. So every substance has, more or less, it has three phases of matter. And so we have solids, liquids, and gases. And so water, even though it's all water, it can have a solid form in the form of ice. It can have a liquid form in the form of water. And it can have a gaseous form in the form of steam. So it's all still water. It just looks different because it's in a different state of matter. And so temperature is what affects the state of matter. If I heat water, if I boil it, it will turn to steam. If I freeze water, it will turn into a solid. And so these graphics here demonstrate the particles of that substance. And so a solid is when the particles are really tightly packed, and so that makes it rigid. They can't move much, but it makes it firm, gives it more strength. Whereas liquid, they're a bit more spread out. They can go with the flow a bit. They'll go to become the shape of the container they're in. They'll fill that container because they've got a bit of flexibility to move around. Whereas a gas, they're just floating around all over the place. And so that's what allows a gas to float in the air and move around the room because those particles are very far apart. And so from this, you would expect that a solid will be more dense than a liquid because it's tightly packed. It's like a rock. A rock is a solid, right? And if I throw a rock in water, rock sinks because rock is more dense than the liquid water. But water is very strange like that because water rocks float in water. Very, very strange. This is unusual. If you have a solid of a substance, it should be more dense. It should sink in the liquid, but water is weird like that. And so in a liquid state, water molecules are really tightly held together by those hydrogen bonds. So because of that cohesion, it's attracted to itself really strongly. But in a solid, once it becomes a crystal structure, like we saw with the salt before, the bonds become a bit more stable and unmoving. And so they actually end up further apart than they otherwise might be because the crystal structure makes it hard for the hydrogen bonds to get in really close and tight like they normally would. And so as a result, the frozen water, the solid, they actually end up further apart than the liquid ones, which actually come together a bit tighter. And so very unusually, water's solid will be less dense than its liquid. And this is what allows me to sip on a lovely, nice glass of Coke with ice cubes floating on top. But it's because of that different density of water, which is very unusual. I'd expect that if I throw water rocks into my water, they would just sink to the bottom, but that is not what we see. And so you're like, cool fact, Simon, who cares? We all care because this allows marine and polar environments to even happen in the first place. But before we get to that, we're going to touch a little bit about heat capacity because that's equally important. So I touched on this before. Heat capacity is the amount of heat energy a substance can take in before raising its temperature by 1 degree per kilogram. So basically, if I put heaps and heaps of energy into water, its temperature won't change much. But if I put heaps and heaps of energy into a metal, it's probably going to get hot really quick. So on the right-hand side here, we can see substances and their specific heat capacities. We can see that to heat up a kilogram of lead by 1 degree, you only need 128 joules of energy. But if I wanted to heat up that water by 1 degree, I would need 4,186 joules. So that's 40 times more energy to raise it by the same amount of temperature. And so water is a great coolant because it's just a heat sponge. It just sucks it up and not much changes. Its temperature is difficult to go up. That's why it takes forever to boil my pot of water on the stove to cook pasta, because it's just so good at absorbing that heat. It doesn't want to go up in temperature. And so this is really useful too in terms of insulating if you want to keep an temperature constant, like we mentioned before. And so in a sub-zero environment, like if I'm, polar ice caps, that kind of thing, this becomes really important. So ice, because of its unusual density, it allows it to float. This is why we can have icebergs. This is why we can have glaciers. This is why we can have anything on top of the water at all. So having ice on top provides a ground for those animals to survive on, where there isn't normally any ground at all. If that ice melts or if that ice sinks, they've got nowhere to go in terms of land. And water's high specific heat capacity in both the water of the ocean and the ice of the land masses allows it to absorb huge amounts of energy without freezing. And so this floating ice acts as an insulator to the cold water underneath. It ensures that the ocean doesn't freeze at those points or rivers, lakes, whatever it might be. It allows the water underneath to stay liquid. And if you're a fish, you really want the water to stay liquid because you're going to be stuck there for a while if it freezes. And you're probably not going to be able to get the food you need, do the processes you need. You may well die. So floating ice allows these marine ecosystems to exist in the first place because it allows water to be a liquid so that things can move around and do what they normally do. And so here's a little graphic of that. So we've got snow on top, we've got ice. That ice is just floating instead of sinking because water is weird like that. And it allows these ecosystems to happen. So there's these little cracks where little microbes can live. There's going to be little fish floating around on air that aren't frozen at this moment. That's helpful. There's also Antarctic krill. So they're like little prawn kind of guys. They float around in big colonies. And then the phytoplankton too. And so if that ice did not float, these would not be insulated in the way they are, and that water would be at risk of freezing. These animals could not do what they do. And so these animals are important because they provide food for other ecosystems. So the krill feed the whales, and the whales migrate. They go elsewhere and do other things in other ecosystems. So we need these sub-zero environments to support that alongside other, so that they can participate in other ecosystems and support them as well. We also need the phytoplankton because, like plants, they absorb energy from the sun. They take energy from the sun, put it into the ecosystem. They get eaten by other things, and those other things get eaten by other things. That's how energy passes through the food chains, that energy coming from the sun. Because if that energy from the sun just hits the water, it's just going to not do much. It might heat the water slightly. But the phytoplankton, because they have liquid water, they can take that energy and introduce it into the ecosystem for other organisms to use as well. All right, so ice is really important. Water is really important. It helps these ecosystems to exist, and these ecosystems are connected to other systems around the world in a wider way. And so that, as a result, means that, climate change is a concern, because if those ice caps melt, the Earth loses that insulation. And as the Earth gets less insulation, it heats up even faster, which results in more ice melting, which means less insulation, which means more melting. And so it ends this positive feedback loop. It just spirals out of control. Positive meaning it just keeps getting worse and worse, not that it's a good thing. Yeah, and so the more melting we get, and it can spiral out of control. Not only that, in addition to the ice caps, there's permanently frozen ground called permafrost. And when that ground is thawed, it releases greenhouse gases in the atmosphere. And so greenhouse gases have been shown to also insulate the Earth and trap lots of heat, which also heats up the Earth more, which also thaws more permafrost, which releases more greenhouse gases, which results in more warming. And so again, we have another death spiral from permafrost as well as the ice caps. So we're in 2 death spirals. That's good. And then there's so scientists theorize all this stuff is happening, and basically there's got that as a result they theorize that there is a point of no return where we could stop burning all the coal, all the petrol in cars right this second. It's too late, doesn't matter. It's spiraling out of control. There's nothing we can do to stop it. And so that's why there's a lot of urgency in climate change as a preventative means, because there's a point where it's going to be a runaway train as a result. And so this is Arctic sea ice volume for every month of the year. So the different colored lines are different months of the year, because obviously there's going to be more ice in winter and less ice in summer. That's just how the seasons work. But we can see that as time goes on, so over the years, moving around clockwise, they get closer and closer to the middle, which indicates a smaller amount of sea ice as a result. And so as we go over time, it gets closer to the middle, it spirals, it spirals, it spirals to the point where, in theory, there's probably not going to be much ice left, if any. And so this is being termed the Arctic death spiral. That's lovely. Yeah, so over time, scientists have been able to clearly measure reductions in that ice. We're starting to see those effects that we're concerned about before. And as a result, we're seeing less insulation in those ecosystems so that they can function and do the things that we need to do. All right, so moving on to something else, just quickly, the water cycle. So you probably learned about this in school too. There's water in the ocean, gets evaporated by the sun, it hangs around in the clouds as condensation, and then it precipitates as rain and goes back down too. And so obviously this is really important. Plants need water to grow. We need water. The animals need water. To get it from the ocean and to make it not salty and to get it to where it needs to be, we need the hydrologic cycle of water to happen as well. So simple stuff, but can't overemphasize the importance of it. And then lastly, on water and the weather. So I mentioned before that water is the only substance which is solid, liquid, and gas on the Earth's surface. And so its freezing and boiling points are just perfectly placed to ensure that the water cycle can do its thing. We've still got some frozen ice for the ecosystems. We've got liquid water, which we can use and drink, but it also needs to boil at a low enough point that it can actually evaporate as a result of the sun, so that it does move around. So it's freezing and boiling points are what allows it all to move through all the states, so that water always gets to where it needs to be. And so, interestingly, the hydrogen bonds of water actually cause it to resist evaporation to some degree, which is good because we don't want the whole ocean in the sky. That would be bad. And so water actually resists evaporation a lot compared to other things, which is good because there's a lot of water out there. The ocean is what, 2/3, 3/4 of the Earth's surface. That's a lot of potential for evaporation from the sun. So it actually resists that a bit, so it's not too much. The hydrogen bonds are helping out there a bit. And so obviously these motions, because water is really good at resisting temperature change, it's a means of insulating the planet so things don't get super cold or really super hot. Water just helps to kind of level things out, whether it's in the rain, whether it's humidity in the air, whether it's the oceans, the waterways themselves as well. And this motion is important too, so that water doesn't go stagnant. We know if water just sits there, it grows mozzies and turns green. It's gross. So we need that motion to stop bacteria and algae and gross gnarly things from living in the water. And so this motion through the water cycle allows that water to stay clean and fresh as well, so that we can use it as we need to. All right, so in summary, water is unique and its characteristics are perfectly designed, which allow it to play all those important roles. And there are many more that I didn't have time to talk about. So water is clearly part of a really perfectly designed and balanced system. God has really outdone himself in just making one substance that does all these things. It just happens to be everywhere. It just happens to be safe. It just happens to be important. And it's just this all-round superstar that can do everything. And it just happens to be one of the most common things on our planet. It just happens to be everywhere, the thing that we really need. And so God's done well. He's designed it perfectly. It's a reminder for us to drink plenty of water too. We now know extra how important it is. But while it is plentiful, having clean and fresh water, we do need to manage these resources carefully as well. So it's there, but we've been gifted with being stewards of that resource, and we need to think very carefully about how we use it as well. So there we have it. We've talked about the key properties of water. We've talked about the chemical structure of it, which allows it to happen. And we've looked at a huge range of impacts on life and why God has done an amazing thing in creating water so that we can have the life that we have on Earth. So thanks all for listening in. It's been a pleasure once again, and I'll chat to you next time.